Welcome everyone to today's video. We are going to begin with a new idea in the chapter of wave optics. Thin film interference. What does it mean? We have a very thin film of oil or some liquid. Now, this oil is usually kept on a surface whose optical density is lesser than that of the oil or the liquid itself. So, its optical density is, let's say, N1, and the surface on which it's kept is of optical density is N2. So we can say N1 is more than N2. Above that we have air whose refractive index is nearly 1. Thin film interference is the phenomena that when we observe some rays of light getting reflected and refracted from this first surface. So ray of light are coming like this. This is the incident ray. It will get reflected from the first surface. This reflected ray will undergo a pi phase change. This second ray will get refracted and it will get reflected back into the medium it came from. This ray upon reflection here does not get any uh, phase change. So why is that? Why does this ray undergo phase change and this ray does not get phase change? It's because we are entering from a rarer medium to denser medium, the reflected ray has some phase change. It gets reflected back by the creation of electric field and magnetic field here, which are in opposite phase to the incoming wave. So there is a phase change. When we go from a denser to rarer medium, there is no pushback onto the electric field of the original ray. So there is no phase change when the ray of light gets reflected in the same denser medium. The ray keeps going on just like that. So film interference is observed in this reflected ray number 1 and reflected ray number 2. These two rays, they interfere at some forward point or at some point uh, ahead. Basically, when they interfere, what will happen is that they produce that pattern of constructive and destructive interference, but they depend upon a condition. Let's say this distance is d only. So this distance d is the oil thickness, liquid or sheet thickness. We say mu into t. This is the optical path to this particular distance when ray traveled from point A to point B. When ray travel from point B to C, there is an additional optical path of mu t. So this is the extra optical path traveled by this ray. This extra optical path is what contributes to the phase difference. Phase difference due to optical path. Taking into account the phase change which is happening here, this pi phase change and this phase change, we can say for constructive interference. This condition gets reversed if the medium beneath the sheet or the refracting medium is a denser one. If this is a denser medium, there is a phase change here as well. So the conditions can get reversed. So let's do a question on this. So we have a white light with uniform intensity across the visible range. 430 nanometers to 690 nanometers, that is the visible range. It is perpendicularly incident on a water film of index of refraction 1.33. So the conditions were 2 mu pi d is equal to lambda into n for destructive interference, and 2 mu d is equal to uh, n plus half into lambda for constructive interference. That is what we must apply. And thickness d equal to 320 nm. So this is the question uh, in which water film of refractive index 1.33 is there and thickness 320 nm, that is suspended in air. At what wavelength is the light reflected by the film brightest to an observer? Brightest means we have to apply the condition of constructive interference. So let's say we know 2 mu t n plus half into whatever wavelength we have. For that we'll find what is the uh, particular wavelength required which will produce a PLR brightest. Refractive index is given as 4 by 3. Distance d, thickness is given as 320 nanometers. So this gives us 8 into 106.6 nanometers. This is half. So the key part of the question is we have to find those values of lambda for which this value lies between 400 to 700 nanometers approximately. So if we calculate this, this value will be some 857 nanometers. So this becomes 854 nanometers divided by this. If we put n equal to 0, this is definitely more than 1000. If we put n equal to 1, let's see what happens. So this is the answer, 570 nanometers. For that wavelength, we'll have uh, the brightest appearance of the colors from this thermal interference. So thank you for joining. Have a good day.